Hello, my name is Tony Lentz with FCT Assembly, and I'm going to present to you Fill the Void. It's a way of mitigating voiding in solder joints. Here is an outline or agenda for this presentation. First, I'll go over a brief introduction on voiding and the types of voids that are possible in solder joints. Then we'll review the factors that can influence voiding. There are many factors. There are many things that have to work together to either create or reduce voiding. Then we'll discuss in detail the voiding results that we found in our experimentation, and I'll summarize with what we have learned about voiding. Then we have a lot of future work planned, and I will discuss what types of variables we're going to test in the future for voiding experimentation. And I have some acknowledgments for people that helped work on this project, and I'd like to thank them for their efforts. And then if you have any questions about this, please email or call us, and we'd be happy to answer any questions that you may have. Do you have voids in your life? Good news is we have solutions to help fill the void. Here's a definition of voiding from the dictionary. It's a completely empty space, like the black void of space. In the world of electronics, a void is a gap in the solder joint where the solder does not fill the space completely, like what is shown in these images below. This is a fairly large void in a BGA sphere. And on the right, we have a top-down view of a BGA component with a lot of voiding in the spheres. Here's a diagram taken from IPC 7095, which is the standard for design and assembly process implementation for BGAs. This diagram reviews the various types of voiding that are possible in a solder joint. Void type number 1 has different sizes, and these voids are somewhat randomly distributed throughout the solder joint. These are called macrovoids, and that's the type of voiding that we're studying in this work. Void type number 2 is shown here at the solder joint to board pad interface. Those are called planar microvoids. They're generally fairly small, and they exist on that plane near the board pad. Void type number 3 is shown on the left side of the solder sphere. Those are cracks or shrinkage voids that are common for SAC 305 and other silver containing alloys. Void type number 4 is shown here in the via and pad. Those are specifically attributed to microvias. Microvia and pad designs are known to create some voiding in the solder joint. And then void type number 5 is shown in the figure below, which are very small microvoids which are located in the intermetallic layers between the copper and the tin of the solder joint. And then void type number 6 is shown up above, and those are very small voids that are actually between the surface finish and the copper of the board pad, and those are called pinhole voids. Those can be created during the finishing process at the bare board manufacturer. Now again, we're studying void type number 1, macro voiding in solder joints. They're a wide range of sizes, and they're somewhat randomly distributed within the solder joint. What about limits for voiding? What are the industry standards for limits? Well, there are clearly defined limits for BGA components, and so I took an excerpt again out of the IPC 7095 standard, and I just wanted to point out this underlying statement here. Some level of voiding in any kind of solder joint is inevitable, meaning there will always be voids in solder joints, but there is still debate as to what is acceptable or an excessive void. So that says right there that voiding in solder joints is going to occur, but we don't have good limits on what's too excessive or what's too much voiding or too large of a void. Now that same standard has charts that do define some limits on voids for BGAs specifically. This void type C is macro voiding, the same type of voiding we were talking about previously. And the limit that I've circled here says up to 100% of the balls may have voids, but the maximum void size in any ball is 25% of the area or 50% of the image diameter. So that's a general rule for all three classes of circuit boards. But what are the limits for other types of solder joints? What about other types of components? There aren't good industry limits for other types of component designs like QFN thermal pads. D-packs with bottom terminated pads or other types of bottom terminated components. So what happens typically is that the end user, the OEM who designed the device, might give the assembler some limit that they have to follow. And the limits can be different based on what type of solder joints that they're looking at. So what we found is a general trend of our customers asking for ways of reducing voiding in general so that they can make sure that all of their assemblies fall within the criteria that are specified by their customers or the end users of the circuit boards. Here are some of the factors that influence voiding. I just want to talk about the major branches on this particular fishbone diagram. Certainly there are a lot of additional factors that are not shown here. I chose this fishbone diagram because it was fairly simple and it highlights the major factors that do influence voiding. The print dispense process certainly plays a role in voiding behavior. The temperature and humidity and the environmental conditions around the solder paste and how the solder paste responds to those environmental conditions can play a role. Water-soluble solder pastes are pretty well known for absorbing moisture out of the air over time. That moisture translates to additional vapor or gas that's generated during reflow, and that can increase voiding. Other types of solder pastes might have an opposite effect. Actually, the longer they sit open on the printer, solvents are evaporating out. They might dry out a little bit, might not print very well, but voiding might be reduced over time. Just in general, though, solder pastes all lose activity over time when they're at room temperature open to the air. And as they lose activity, they're not going to reflow as well. They're not going to wet and spread as well, and that can create voiding. The reflow profile, of course, plays a role in voiding behavior. You've got to use the appropriate reflow profile for the solder paste that you're using. Some solder pastes respond well to long, hot soaks in order to drive off volatile materials and fully activate the solder powder and the board pad and component surfaces. Others do not respond well to long, hot soaks. They might respond better to, say, a higher peak temp or a longer time above liquidus. In any case, the reflow profile has to be tuned in order to minimize voiding with the solder paste that you're using. The substrates or components play a role in voiding behavior. The surface finish on the board pad, the surface finish on the component leads, the oxide level on that plays a role. As oxide levels become thicker, that creates a situation where it's difficult for the solder paste to wet and flow. And if the solder paste can't wet and flow properly, then that's going to create a gap in the solder joint, which is essentially a void. Then the solder paste itself, of course, has a big effect on voiding. In a lot of cases, our customers feel that switching solder paste is an easy way of attacking the voiding problem because they might not have control over some of these other things. They might not be able to change the substrate or component, the finishes that they're using. They might not be able to change the design of, say, the stencil. The print process, there's only so much you can do with the print process. Your solder paste is going to be open for a certain period of time on the printer, regardless of how fast you try to run your production. The printer is usually not the limiting factor. It's usually the pick and place process or possibly the reflow profile. So there's often times you can't control everything in the print process or everything in the substrate component branch. You can certainly control the solder paste and you can control the reflow profile, and those are good ways of trying to mitigate voiding. So the three branches that we're studying on this fishbone diagram are the print dispense process. We studied some different stencil designs to try to mitigate voiding on QFN thermal pads. We studied different profiles, 2 different reflow profiles, and 2 different solder pastes in this paper. Here's a diagram of the stencil design that we used and the 4 different QFN thermal pad designs. So first of all, the QFN that we're using is shown here. It has a matte tin finish. It's a 10mm body, and it has a 68 perimeter leads with a 0.5mm pitch. Here's a diagram of the 4 different stencil designs that we used. We called them U9 through U12. U9 is a standard crosshatch 9 window pane. U10 is that same crosshatch but is rotated 45 degrees. U11 is a 5 dot pattern where we're printing 5 dots of solder paste on the pad. And then U12 is a diagonal stripe pattern. Here's a picture of the printed solder paste on the circuit boards that we're using. Circuit boards have an e-ink surface finish, and you can see the paste here. Here's the 9 window pane print. Here's the 45 solder paste A has more volatile material in it. But again, these two pastes. The equipment that we used is shown here. The printer was set to 30 millimeter per second print speed and a 1 pound per inch blade pressure. The separation speed is 1.5 millimeter per second. The pick and place that we used is shown here. We pick and place the 4 QFN components per board. And then we ran, generally speaking, we ran 30 boards per variation. So we had 30 data points for each component design for each board solder paste reflow profile. So I wanted to gather 30 data points per variation in order to generate some valid statistical analysis on these data sets. The reflow oven that we used is shown here. This is a digitally controlled reflow oven that simulates a 10-zone convection reflow, and reflow was done in an air atmosphere. And then the X-ray and the parameters that we used are shown here. We use box and whisker plots to show our voiding data. So for those of you who are not familiar with these type of plots, I'm going to briefly explain how to interpret this data. So a box and whisker plot has a line in the middle of the box, which is the median value of the data. Then the box itself represents the interquartile range. So 1/4 of the data below the median and 1/4 of the data points above the median are shown by the box. And then the whiskers at the very bottom and the very top are the minimum and maximum values in the data set. So a box plot is sort of like a histogram if you're looking top down on the histogram. The box itself would represent the middle lump or the bell curve part of that, and then the very ends are the minimum and the maximum of the histogram. On the right, here's another diagram that explains outliers. You'll see some of our data sets show some dots above the top whisker or below the bottom whisker, which are outlying data points. And those are determined by how far they are away as compared to the interquartile range size. Here's an example of what our voiding data is going to look like. We have void area on the y-axis and then our variables across the x-axis. In this particular case, we're looking at the 2 different solder pastes that we studied. Solder paste A is on the left, solder paste B is on the right. You can tell solder paste A has a much lower median value than B, and the box and whiskers are quite smaller than they are with solder paste B, so there's a much larger spread in the data with solder paste B. And then here's some representative images of what the voiding looked like. Solder paste A obviously has lower void area than solder paste B. Now we also run what's called a Tukey-Kramer HSD test to compare the significance of the data sets. So this is an honest significant difference test, which tells us whether the data sets are really statistically different or statistically similar. And this is done with a 95% confidence level. The data sets are, first of all, charted up at the top. We've got void area, and then we've got the two variables, paste A and paste B. The data sets are represented by circles. So if the circles do not touch or do not overlap, then the data sets are significantly different. If the circles are overlapping, then they may not be significantly different. When you have a lot of data sets, though, if you're comparing, say, 4 or 5 data sets, quite often the circles are overlapping and it's hard to tell from the graph what's going on. So we use the connecting letters report down at the bottom to help us interpret whether these are really different or not. So the connecting letters report shows each data set in order of mean void area, and then the letter codes This is 5.2% for solder paste A. These are significantly different. So solder paste B is generating higher voiding in this experiment. Here are the voiding results for the stencil designs that we tested. U9, U10, and U12 are all very similar in terms of median and mean void area. U11 looks like it might be a little bit higher, and these representative images sort of show that. U9 and 10 look much lower in void area. U11 looks a little higher. U12 is close to U11, but not quite as high. The Tukey-Kramer analysis proves that that is true. So U11 has a different letter code than all of the others. It has a 28.5% mean void area versus 19 to 21 for all the other stencil designs. So the 5-dot pattern, U11, gave us overall higher voiding than the other designs here. Here are the voiding results for Reflow profile. So we have the ramp to spike profile on the left, the ramp to spike high temp profile on the right. And I should mention that all these charts I've showed you are ignoring all the other variables. I simply split this data up by reflow profile and including all the variables lumped in to each one of these box plots. So overall, these two reflow profiles don't look like they're affecting voiding very much. Here's the Tukey-Kramer analysis for voiding results by reflow profile. And you can see that there is no significant difference here. These circles overlap and the letter codes are the same on the connecting letters report. We're talking about an overall mean void area for the high temp profile of 23% and for the ramp to spike profile of about 22%. So overall, I can say that the reflow profiles had very little effect on voiding, but this is irrespective of all the other variables. When you break this data out by some of the other variables, like for the solder pastes, and you look at reflow profile by solder paste, there are some interesting differences that show up in the data sets. Here are the voiding results for stencil design broken out by solder paste. So here we have solder paste A on the left, solder paste B on the right. Overall, solder paste A has lower void area than solder paste B, as we showed previously. Again, you see U11 has slightly higher void area than the other stencil designs. U11 on solder paste B also shows slightly higher void area than the other stencil designs. phase with vacuum to reflow the solder joints again to see if we could reduce voiding. Here's an image of the vapor phase system that we used. It had 4 different vacuum options that we tested. No vacuum. Then we used what's called main vacuum, which pulls a vacuum during liquidus. And then there's 2 different pre-vac options. Pre-vac 1 pulls a vacuum before the solder paste is even heated to try to remove air from the printed solder paste. Then pre-vac 2 is pulled during heating but before the solder turns liquid. Try to remove volatile materials from that solder paste. Here are the voiding results for the vapor phase with vacuum options. I threw in the data from the ramp to spike convection reflow for comparison. This was done for solder paste B. So solder paste B in the regular convection reflow gave fairly high void area. Say this is a median value of about 38%. When we ran that in the vapor phase system without vacuum whatsoever, that void area dropped quite a bit. You can see how the voiding went down. When we used main vac plus pre-vac 1 and then main vac plus both the pre-vacs, you can see how low the voiding got. The voiding went down to almost nothing with all the vacuum options. So there was a significant reduction in voiding based on using vacuum during this vapor phase reflow. When we look at the Tukey-Kramer results, here's what we saw. The ramp to spike convection profile gave about 37% void area. Vapor phase, just reflowing in vapor phase without vacuum, dropped that down to 23%, and that's a significant reduction in voiding. That's because the vapor phase system operates in an oxygen-free environment. Once the vapor starts condensing over the surface of the circuit board, that circuit board is then sealed with a barrier of liquid to prevent oxygen from getting to the solder joints. And simply by removing oxygen from the reflow can help improve wetting and flow behavior so voiding can be reduced, and that's what we saw here. And then the 3 vacuum options here all dropped voiding down below 2% void area. A significant reduction in void area just by using vacuum. So we did not run a test with a convection reflow with vacuum, but I would expect similar results. Any type of vacuum pulled during liquidus on the solder joint is going to help reduce voiding. Here are the voiding results for using vapor phase as a rework method. So we started off with convection reflow. We reflowed 10 boards, and this is the type of voiding that we were seeing. Relatively high voiding, median value of about 45% void area. And then we took those same exact boards and reflowed them again in the vapor phase with vacuum, and we pulled main vacuum on these. And the voiding area dropped down to this very low level, below 10% void area. So that's like a 35% reduction in void area. And the voiding of the exact same component, this is the before picture, this is the after picture. So in this particular case, we were able to use vapor phase with vacuum as a rework method to reduce voiding. Now I will say that the solder joints looked a little duller and darker after this, after reflowing a second time. The same thing would happen if you were reworking the solder joints with other methods, like a soldering iron or hot air reflow. Anything you're using to remelt and rework a solder joint is going to cause darkening and more oxide on the outside of that solder joint. But we were successful at reworking voids using vapor phase with vacuum. Here's the Tukey-Kramer analysis on that data. The ramp to spike reflow and convection reflow is shown here. The circle's up here, and this other circle after vapor phase with vacuum is much, much lower. So we went from a 43% mean void area down to 9% mean void area. Significant reduction in voiding. So it is possible to rework voids with a vapor phase vacuum system. So what have we learned about voiding? First of all, solder paste B generated higher voiding and larger voids than solder paste A. So there's quite a difference in voiding behavior between these 2 solder pastes. The 5-dot stencil design generated higher voiding and larger voids than the other stencil designs that we used in this experiment. We are going to continue testing more stencil designs to prove that out. The ramp to spike profile generated higher voiding with solder paste A, but the ramp to spike high temp profile generated higher voiding with solder paste B. So you have to tune the profile to work with your solder paste. And then in general, as total void area increases, the size of the largest void also increases, which makes sense. That's intuitively how that works. So here are recommendations on how to fill the void. We recommend that you use a solder paste that generates low voiding in your process. Not every solder paste will work well in every process, so we suggest that you run a test and try some different solder paste to see what will work for you. We also recommend that you optimize the stencil design to minimize voiding. You should work with a good stencil supplier who can help with that. I'm sure your stencil suppliers can recommend different options, different types of cross hatches, different reductions in printed paste coverage on bottom terminated components to help reduce voiding. And then we definitely recommend that you work with your solder paste supplier to optimize the profile in order to minimize voiding. Not all profile changes will work the same with every paste. You've got to use the right profile with your solder paste in order to mitigate voids. Here's the future work that we're planning on doing, and we'll be presenting some of this in Fill the Void 2. We're going to do some additional testing with vapor phase reflow with vacuum with additional solder pastes. We are going to test nitrogen in convection reflow to see if that has the same effect that the vapor phase system did by eliminating oxygen from the reflow chamber. We're going to run a wider array of solder pastes, including a variety of no cleans, to see what effect that has on voiding. We're also going to vary solder powder